In this lecture session, I am going to demonstrate the topic on single phase full wave control rectifier. So, what is the benefit for using full wave control rectifier with respect to the half wave control rectifier? Actually, in case of full wave control rectifier, the average output voltage is just double with respect to half wave control rectifier. That is why the all-over efficiency of the converter circuit, rather the rectifier circuit, that will be better with respect to the half wave control rectifier. As per the circuit connection, the single phase full wave control rectifier can be two types. Number one, that is midpoint converter or M2 connection, and number two, bridge converter or B2 connection. Okay, let me discuss the both by the proper circuit diagram. The schematic circuit diagram, which is represented over here, the first one that stands for the M2 connection and the second one that is for B2 connection. In this case of M2 connection for the single phase full wave control rectifier, which is normally constructed by the transformer, and the primary part of the transformer that is connected to the supply voltage, where the supply voltage can be defined by Vm sin omega t, and the current in the primary side, that is Is, and the secondary coil that is center trapped and which is actually connected by the R load, as we are going to discuss about the single phase full wave control rectifier with R load. And two thyristors are there, that is T1 and T2, and which is connected in this manner. So, as the center tap transformer are used for M2 connection, that is why the upper part of the first part, that is actually plus and this one is minus. In case of the lower part, it will be plus, it will be minus. That means we assume the number of turns in the first part and the number of turns in the lower part both will be same, as it is center trapped. So the voltage will be appear that is equal in magnitude. It will be Vs and it will be Vs, and the current which is flowing through the resistance or the load that is supposed defined by I0, and the voltage appearing across the resistive load, that is assumed V0. This is all about for the M2 connection. Now for B2 connection, in this case we are using four thyristors T1, T2, T3 and T4, and they will form a bridge circuit. That is why the name stands for B2 connection. And the supply voltage, that is AC supply, is given over here. The magnitude, that is the expression, that is Vm sin omega t, and the current, that is circuit current, that is defined by Is, and the voltage across the load or the resistance, that is defined by V0, and current to the resistance, that is defined by the I0. So this is all about for the B2 connection. Now in case of waveforms, we have taken the all parameters that is from M2 connection. Number one, that is Vs, which is called actually supply voltage, that is Ig1 for the gate pulse for the first thyristor, Ig2, that is gate pulse for the second thyristor, V0, that is the output voltage across the load, that is I0, that is output current which is flowing to the load, Vt1, that is terminal voltage across T1, and Vt2, that is the terminal voltage across thyristor T2. So this is all about for the waveforms. Actually, this waveform can be considered for the M2 connection only. If the waveform can be considered by B2 connection, then there will be small changes. We should taken the extra two gate currents for another two thyristors, as in case of the B2 connection there are the four number of thyristors are there. That is why the current should be, the gate current should be 4 in number. That is why we can be represented by Ig1, Ig2, Ig3 and Ig4. And a similar way, okay, we can represent the both thing in case of the M2 and B2 connection. But actually the output voltage pattern and the output current pattern almost similar for the both purpose. That is why we are going to demonstrate this thing through a particular circuit which is taken from M2 connection. Now, let we understand the working principle. As the supply voltage is AC, that is why when the voltage goes positive for the positive half cycle, then the current starts flowing to the primary coil of the transformer, and due to mutual inductance, then the secondary coil will be energized as it is center tapped. That is why, as well as we can say, as the number of coil in the first part and the number of coil in the second part both are same, or number of turns ratio are same. That is why voltage appearing in the upper part, that should be Vs, as well as the lower part should be Vs, and the polarity will be this one positive and this is negative. Similarly, in the lower part it will be positive and it is negative. When we are applying the positive half cycle, means in case of supply, the upper part will be positive and lower part will be negative. In case of the negative half cycle, so obviously the direction of the polarity will be changed, then it will be positive and it will be negative. Similarly, it will be again reflected on this particular secondary winding. That means, and that particular case, it will be negative, it will be positive, it will be positive, then it will be negative. Similarly, for the lower part, it will be positive and it will be negative. So in case of positive biasing condition, what happen when Vs can be occurred in this first part of the transformer, as it is positive, then the current try to flow in this direction. That means the thyristor T1 should be in forward biasing condition, as well as suppose we are applying the gate pulse across the first thyristor, then it will be triggered. Once the thyristor T1 will be triggered, then immediately the supply voltage will be reflected on the load terminal. That means then VO, that should be equal to Vs. Okay, in this particular case, what happened, as the lower part of the transformer secondary coil, current try to flow in this direction, but in this particular case the switch or the thyristor T2 is in reverse biasing condition. That is why T2 will not be turned on. That means for positive half cycle, only T1 starts conducting and voltage appearing across the load, that should be Vs. Okay. For negative half cycle, when the supply voltage goes negative, then this part will be negative, positive, and the upper part will be negative. That is why automatically the polarity has changed in this particular secondary coil. That is why just I told you before, that is the lower part will be positive, upper part will be negative. Similarly, for the lower part of the transformer, it will be positive and it will be negative. Then current try to flow in this direction. That is why then T1 will be in forward biasing condition. Then by using the appropriate gate pulse across the thyristor T2, once the thyristor T2 will be fired, then the current starts flowing to this direction. That means by using the forward biasing SCR T2, then the current Vs, then the voltage Vs, that should be appear across load. In that particular case, what happened, as this part in case of the upper part of the transformer secondary coil, if it is positive and it is negative, then current try to flow in this direction, that is not required. Because what? Because of then T1 will be in reverse biasing condition. That is why in this particular case T1 will be in off condition and only T2 starts conducting. That means we can conclude in case of M2 connection, for positive half cycle T1 starts conducting, then T2 was in off state. For negative half cycle, T2 starts conducting, but T1 will be in off state. In the similar way, we can explain the the working principle by using B2 connection. But here as we are using the 4 SCRs, that is why T1 to T2 will be fired first, then the question for T3 and T4. That means when the when the supply voltage goes positive, when the current starts flowing across T1 and across T2, and we are applying at the same time we have applied the triggering pulse across thyristor T1 as well as the thyristor T2 at the same instant, then the current starts flowing from the supply to T1, then load, and coming back from load to T1 to the supply. This will be the direction of the current. Okay, that can be happen for a first positive half cycle. When after crossing 180 degree, as per the normal nature of the sinusoidal wave, when the supply goes to the negative part, then we should apply the triggering pulse across the thyristor T3 and T4. Once the thyristor T3 and T4 will be triggered, then the current starts flowing in opposite direction. As after 180 degree the supply voltage goes negative, then current starts flowing to this from supply, then to T3, then across load and coming back to T4 and to the supply. So in this way the total operation can be performed for M2 and B2 connection. Now the entire operation can be demonstrated by the waveforms also. See, when we are applying the AC signal, that is why this is the waveform of the supply voltage. Is a pattern is sinusoidal wave. Okay, and we are applying the triggering pulse across the thyristor T1 during positive half cycle. That is why Ig that is given on the positive half cycle again for the next positive half cycle in this way. And we have applied the triggering pulse across thyristor T2 during negative half cycle. That is why the T2 should be given, Ig2 should be given across T2 during negative half cycle. And next will be reflected on the negative half cycle in this way. That means Ig1 is given only during the positive half cycle and Ig2 should be given only during the negative half cycle. Okay, as it is working as a full wave rectifier, that is why for the both cases, for positive half cycle as well as in case of negative half cycle, in the both way the current starts conducting and the direction of the current across the load remaining in the same position, that is right hand side to left hand side. That is why it can working as a rectifier, and the output voltage as well as the output current peak that should be double with respect to the half wave rectifier. Okay. Now see, once we have applied the triggering pulse alpha at this particular point, then immediately thyristor T1 will be fired. Once the thyristor T1 will be fired, then the voltage, means I am talking about this voltage, that is plus Vs, that should be appeared across the resistance, and the direction of the current, that is in this way, which is defined by this arrow. That means across load, that is right hand side to left hand side. So similarly that can be represented by the waveforms also. That is why once the thyristor T1 is triggered at this point alpha, then the load voltage that should be followed by the input voltage or supply voltage. That is the same waveform that will be reflected on the load voltage also. As well as next triggering pulse is given on this particular case, then it will be repeated when the next cycle onward. At the same time, when the supply voltage goes negative, suppose after pi 2 pi by 2, what happened? Then thyristor T2 is fired, as we are given the get pulse across the thyristor T2, that is alpha, that means pi plus alpha. That is why in this case thyristor T2 will be fired. Once the thyristor T2 will be fired, then automatically the current starts flowing in this direction, as in the negative half cycle, in this direction. That means immediately the supply voltage that should be followed over the load. That is why in the previous case, just like a previous case, the supply voltage that will be followed over here. As we are using the reverse biasing, still the supply voltage both are in the same direction, just like before. Why? Because in the first case, when T1 was triggered, then the polarity of the voltage across the load, that is this one is positive and this side is negative. And again when T2 is fired at the negative cycle or negative half cycle, then again the voltage is appeared, this one is positive, this one is negative. That means if we assume across the load, but the both cases the polarity of the voltage, the right hand side is positive and left hand side is negative. That is why we can say for the both case the load voltage remaining same. That is why we have drawn this load voltage for positive half cycle and negative half cycle, both are in same direction. Okay. Now I am talking about the current waveforms. Okay. Here actually we are using a resistive load. That means what? We know the phasor diagram of resistive load. That is what? That is actually, in case of resistive load, we know voltage and current both are in same phase and in a same state line. That means we can say, if we consider the voltage waveform that is defined by this axis, so the current, that is, as we know, the current equal to, that is V by R. That means the current waveform and the voltage waveform both will be same. That is actually defined by the phasor diagram of the resistive load. That is why I, the nature of I, that should follow the voltage waveform. That is why the waveform of the output current and the waveform of the output voltage both will be same for the application of the resistive load. Now I am talking about the terminal voltage. See, there is very interesting part. In case of the forward biasing condition, or when the supply voltage goes positive during first positive half cycle, then T1 was triggered, right? Then the supply voltage is appeared across the load. Okay. At this particular case, T1 was in reverse biasing condition. That is why T1 was stopped conducting and it was in off state. That is why total voltage that will be appear across T2. That means when T1 starts conducting, then the voltage will be appear across load as well as the other voltage that is defined by the lower part of the secondary coil of the transformer that should be occurred on the T2. That is why I am talking about this part only from alpha to pi. When T1 is triggered, means Ig1 is triggered, that means the voltage across the first load, that is this one. That is why the Vt, that means Vt turned on, that means it is working as a short circuit. That is why no voltage is appearing across Vt. That is why up to this point, when the T1 was triggered or working in on state, then the low voltage is across T1. At this particular point, obviously the voltage is appearing across T2 as it was in off state. Up to the which point? Up to the next triggering pulse is given across T2 for negative half cycle, that is pi plus alpha. So up to this region, the voltage appeared across T2. Similarly, on the other hand, we can say when T2 starts conducting at the point of pi by plus alpha to 2 pi, then what happened? Then the total voltage is appearing across T1 and no voltage is appeared across T2 as T2 is in on state and it is working as a short circuit. That is why no voltage is appeared across T2 during this duration, that is pi to 2 pi plus alpha, and that particular case the voltage is appeared across T1. So in this way it will be continued up to next cycle onward. So we can conclude this: when T1 starts conducting during positive half cycle of the supply, then the voltage will be blocked by the T2, and when T2 starts conducting for the next negative half cycle, then the total voltage will be blocked by T1. So in this way it will be worked during the operation. The total thing can be happen for B2 connection again. Only we have changed the axis, that is VT1 and VT2. It will be replaced by VT1, VT2, and it will be replaced by VT3, VT4. But other remaining parts are same. So from the waveform, it is found that in a complete cycle, if we are talking about 0 to 180 degree, the number of peaks in the forward direction, that is 2. In case of the half wave rectifier, the number of peak was 1. That is why the average output voltage from this full wave converter, that should be double with respect to the half wave converter. So as it is working as a rectifier circuit, that means input voltage, that is AC, it should be converted in terms of DC. That is why we are going to calculate the average output voltage and RMS output voltage. We know how we can form the expression for average output voltage. That was discussed in my previous lecture so many times. That is average output voltage from any kind of periodic signal that can be replaced by number of peaks in any direction divided by total cycle integration of confined region. That means the peaks which is confined to a particular limit, that is why I am trying to say that is integration of confined region, then voltage expression d omega t. In the similar way, we can represent the total average DC output voltage through this expression. That is VDC, okay? That is the average output voltage defined by VDC. That should be equal to number of peak by complete cycle. So go to the waveform. Number of peak in a complete cycle, that means in case of the voltage waveform, if we are talking about 0 to 2 pi, this is a complete cycle, and a number of peaks in any direction, suppose in forward direction, that is 2. That means this is the number of peak. And one peak, consider any one peak, suppose this one, it should be confined between two limit. So this point is actually alpha and this point is actually pi. So we can say the expression will be, that is number of peak by complete cycle 2 pi integration of alpha 2 pi, and the expression of this particular wave that is coming out from the voltage expression at both are similar, output voltage and input voltage, due to presence of the resistive load, that is Vm sin omega t d omega t. So the complete expression for the average output voltage, that should be defined by 2 by 2 pi integration of alpha 2 pi Vm sin omega t dt. And after simplification, we will have the expression that is Vm by pi minus omega cos omega 2, that is the integrating part of sin omega t, that is minus cos omega t, and that is alpha to pi. So considering the limit after modification, we will have the expression that is Vm by pi 1 minus cos alpha. So this is the expression for the average output voltage of the full wave rectifier circuit during R operation. Now I am talking about the RMS value. So first we can calculate the IDC. IDC means VDC by R. So we can write the expression IDC, average output current, from the converter circuit or rectifier circuit, that is VDC by R. That means VDC means Vm 1 plus cos alpha by pi and divided by R. So this is the expression for the average output current. Okay. Now how to calculate the RMS value? The simple calculation, as we all know, that is RMS defined by the root mean square of the original supply voltage. That means that can be defined by Vrms equal to 2 by 2 pi. At a similar way of the average value calculation, number of peak by complete cycle, integration of alpha 2 pi, that is the square of the voltage expression, Vm square sin square omega t d omega t, and under root. So that is why root mean square of this expression or the average expression, that will give us the RMS value of output voltage. So after simplification, we can have, that is 2 by 2 pi Vm square by 2 is a common part, and that is divided by 2 and multiplied by 2, that is 2 sin square omega t d omega t. That is why we can rewrite the expression 2 sin square omega t means 1 minus cos 2 omega t. So the expression will take this form, that is Vm square by 2 pi integration of alpha to pi 1 minus cos 2 omega t d omega t under root. Okay. Then by integrating the thing, we can have, that is 1 integration, that will give you omega t, and the integration of cos 2 pi, that will give you 1 by 2 sin 2 alpha, cos 2 omega t, that will give us 1 by 2 sin 2 alpha, sin 2 omega t. That means we can write the expression that is Vm square by 2 pi, that is omega t lower limit alpha to pi minus 1 by 2 sin square omega t lower limit alpha to pi under root. So further modification, we can have the result that is Vm square by 2 pi pi minus alpha plus 1 by 2 sin 2 alpha. Okay, by considering all the limit, that is alpha and pi. So we will get this expression. Finally, after modification, we will get the final expression of the RMS value, that is Vm into pi minus alpha by 2 pi plus sin 2 alpha by 4 pi. So this is the under root, that is the final expression of the RMS value. In the similar way, we can calculate the RMS current also, that is defined by this expression, that means Vrms by R, that means Vm by R, that is pi minus alpha by 2 pi plus sin square 2 pi by 4 pi under root. So this is all about the discussion about single phase half wave control rectifier with RL load. Thank you.